Hi, my name is Konstantin Knizhnik. I'm working for Postgres Professional. Let's speak about Postgres future, more precisely about using Postgres for OLAP. Traditionally, database systems are split into two camps, optimized for OLTP and OLAP processing. Most of well-known databases as Postgres, Oracle, SQLite, well, first of all, optimized for OLTP. Right now, there are several products optimized for OLAP, like Greenplum, Teradata, Clickhouse, Vertica. But them are very slow when you try to perform frequent updates. It leads to so-called Lambda architecture, when input data stream is split into two directions, into two data stores. One is used for real-time processing and one is used for batch processing. But now many customers needs real-time analytics. They want to be able to execute analytic queries for most recent data. This is why there are several products offering both OLTP and OLAP. It's called hybrid transaction analytic processing. I didn't finish this list because many traditional databases also offer them can be used for OLAP. The same is true for Postgres. Let's check how is it really true and how good is Postgres for OLAP. For OLAP, most critical is executor speed. OLAP queries need to process large volumes of data, and speed of executor is very important. Unlike OLTP queries, which using indexes are dealing with small number of records, OLAP queries are used to perform aggregation among large volumes of data. There are two popular approaches of improving executor speed and reducing interpretation overhead. First one is just-in-time compilation, and second is vectorized executor. Right now, Postgres includes JIT, and let's see how good it is and how it's comparable with vectorized executor. Why Postgres is slow on OLAP queries? It is still, even with JIT, about 10 times slower than specialized OLAP databases like Hyper. First of all, there is a high tuple unpacking overhead. Interpretation overhead, which is mostly reduced by JIT, but still not completely. Also, MVCC, which is very important for OLTP, it's at significant overhead for OLAP. Both speed and space overhead. This is the typical profile of OLAP query. You see that most of the time is spent is tuple deforming, and at the second position is interpreter. This is profile without JIT. Let's look at Postgres plan of query execution. It's very simple query performing aggregation with simple filter. Each node of this plan requires several function calls, and them has to be performed for each record of process table. This is illustrated at this picture. So we perform calculation for each record and for columns of each record, and Each operation requires several function calls. We can significantly reduce interpretation overhead if we will perform operations not with scalars, but with tiles or vectors. Each operation is implemented as very efficient loop written in C, and so speed of execution operation in this loop is comparable with native code, and interpretation overhead is still present, but typical size of vector is about 100 or more elements, so it is interpretation overhead is reduced 100 times. How to get these vectors? They can be instructed from standard Postgres heap, but it is inefficient. It's much more efficient to store data in vertical format, so-called columnar storage. Postgres have several extensions for providing column storage. It's first of all C-store and a new one, Z-store. I took Vectorized executor extension, and it was available for Postgres 9.6 and ported it to most recent version of Postgres. For 9.6, it provides quite reasonable improvement, about 2 times speed up of TPCH query 1. This is quite small database, just 10 gigabytes, which completely fits in memory. Master version of recent version of Postgres is much faster on this query comparing with 9.6, mostly thanks to JIT and other improvements in executor. So it is about 2 times faster than Postgres 9.6. Comparing with this phone, vectorized executor is provide not so noticeable improvements. So it's 15 seconds comparing with 16 seconds. Also, vectorized executor is implemented as a foreign data wrapper, and right now it doesn't allow parallel plans execution. This is why these results are missed. Maybe it's because of large overhead of extracting vectors from Postgres heap. I try to integrate this vectorized executor with Z-store. Z-store itself, the vectorized executor, provides slightly worse performance comparing with vanilla Postgres with standard heap. With vectorized executor enabled, it is slightly faster, but still slower than vanilla Postgres. It does not mean that columnar store, particularly Z-store, is not cannot be useful. It should be useful and provide high performance improvement if data size is large and much larger than size of main memory. In this case, compression and execution of columns on extraction of columns on demand provided by that store will be much more important. Let's speak about another problem. We need to be able to store a big, huge stream of input data. Postgres is able to execute inserts quite fast, almost with the linear speed of writing to the disk, but only in the case when there are no indexes. When there are indexes, and especially when them do not fit in main memory, then insertion speed is decreased very fast. But we need indexes to be able to execute, efficiently execute most of other queries. So what can we do in this case? And there is answer LSM, logical structured merge tree. The idea is very simple. We keep small fraction of index in main memory, and all inserts are done only in this small part of the index. Periodically, this in-memory part is merged with on-disk parts. And the main idea is that it is performed in background and does not stop inserts. The most popular database now using LSM is RocksDB. It is widely used, it's key-value database, widely used for many other databases on top of it, like Cockroach, YogaBase, and many others. There is a foreign data wrapper for RocksDB for Postgres. I took this foreign data wrapper and improved it by providing concurrent execution of operations and compare it with the standard Postgres inclusive B3. I just did 215 millions of inserts with random keys and 8 begin fields emulating typical record lengths. At the beginning, B3 was faster than LSM, but when index is not fitting in the main memory anymore, B3 degrade very fast, and for LSM provides almost constant level of performance. Finally, final TPS are 15 times better for LSM than for Postgres B3. It just for one client. For 10 parallel clients, results are slightly worse, just 6 times advantage, but it is still very important. I also compared it with native RocksDB, and performance is similar, so overhead of foreign data wrappers wrapper is not so large. But you should realize that this foreign data wrapper is storing all data outside Postgres, so all isolation, atomicity, and durability is provided by RocksDB, not by Postgres. Definitely, we need to have such data inside Postgres itself. I tried to make some experiment and simulate LSM using standard Postgres B3s. I have 2 B3s, one small which used to fit in main memory, and bigger one which contains most of the data. All inserts affecting only are done within memory B3. When size of this B3 reach some threshold value, it is merged with main index. To avoid blocking of inserts at the moment of merge, we need yet another in-memory B3. So finally, we have 3 B3s. One is active used. One is merging in background with main index, and main B3 is keeping all the data. Certainly, select has to access all these 3 B3s, but as far as these 2 B3s are in memory, overhead is not so large as can be expected. To the table mentioned above, I added results for LSM3. I called it LSM3 because just contains 3 B3s. So performance is comparable with RocksDB LSM. It's 16 times faster for one client. Result for multiple clients are much worse, mostly because of high Postgres log contention overhead. But you need to understand that this is not final solution, just prototype. Definitely, B3 is not completely simulate through LSM3 because it cannot avoid random reads completely. Just try to reduce number of such reads because of better data locality. Next problem, write amplification problem. I hope everybody heard about Uber story, how them switch from MySQL to Postgres and back from Postgres to MySQL. One of arguments was that in MySQL, secondary indexes are referencing keys of primary index, and in Postgres, them has direct pointers to the heap. And so update of, when we create new, Postgres create new version, all the secondary indexes has to be updated. This is how indexes are organized in Postgres. So B3 index has several entries for each version of record. And using visibility rules, we select one which match the current transaction snapshot. Right now, Postgres is solving write amplification problem using hot updates. If update is not affecting queues of any index, we can keep just one reference in B3 to the head of hot update chain. And other versions are included in this chain and not requiring updates of indexes. But there is still limitations of hot update mechanism. You can see one of the obvious case when a record is not fitting at the same page. We have to put it on another page, and in this case, secondary indexes has to be updated. Another Postgres bottleneck or some kind of some source of inefficiency is toss data when record size is large enough and it is not fitting in one page, then data is split into chunks, and these chunks are placed in toss table. Toss table is just mostly like normal Postgres table, which is connected to main heap table using block number and TID key. And toss number attribute is used to extract chunks in proper order. Size of chunk is about 2 kilobytes. And so extracting of large blob requires fetching several large number of records. I try to create extension, I call it UNDAM, based on Postgres table access methods. UNDAM stands for Undo Access Manager access method. The idea is to perform updates in place and use undo chain where transaction can locate all the versions of updated record. UNDAM use split records into fixed size chunks, and data is stored into two forks, main fork and extension fork. Chunk headers are stored in main forks, and these chunks are updated in place. And all indexes has references to these header chunks. Undo chain is a list of undo versions, single linked list of undo versions, and each undo version also contains a chain of extension chunks. As far as all chunks have fixed size, we can use fixed size allocator. Each block contains a bitmap of 3 chunks, and blocks with 3 chunks are linked into double linked list, and allocator is traversing these blocks. Certainly, UNDAM storage provides the best results for update workload. When I create update-only test, which use PGBench schema and just perform random updates. As you can see, UNDAM provides up to 2 times performance improvement comparing with standard heap. I mentioned the result for logged and unlogged tables because it is one of the bottleneck of UNDAM implementation. It has to use generic val records, and this mechanism currently is not so efficient. It adds large overhead because it has to compare 2 pages to be able to build delta sequence for updated record. And this overhead is quite significant, and this is why for standard PGBench test, performance of UNDAM for logged and unlogged table is significantly different. But for update-only workload, this performance is not so large. Let's now talk about OLAP hypercubes. This is old approach for building analytic systems. Previously, hardware and databases were not fast enough to be able to execute, to perform aggregation for large volumes of data in reasonable amount of time. The only solution was to pre-calculate these results and store them in database. This is how OLAP hypercubes are organized. Right now, this solution is not so popular, and mostly because of columnar store. Columnar store allows to calculate aggregates very fast, and there is no need to pre-calculate them. But I do not think that this idea of hypercubes is completely dead. Maybe it can be reincarnated on new level. This new level is called materialized views. A little bit about history of materialized view in Postgres. Standard SQL views were introduced from the very beginning, but it's just syntax sugar for simplifying writing queries. Materialized view were first implemented in Postgres 9.3. Just normal table with some refresh mechanism. The problem is that refreshing of materialized view can take comparable amount of time with building view from the scratch, and even more. And right now, there is a prototype implementation of incremental materialized views, which using triggers mechanism. And in this case, materialized view is up to date with main table. So we can combine OLAP and OLTP. But let's perform how efficient it is. OLAP is usually doing some kind of joins with group bys and aggregation. So let's create some materialized view using PageBench schema. It just calculates sum of balances for tellers. Creation of database, initialization of database takes just 26 seconds, and almost the same amount of time is needed for building incremental materialized view. When we need to get results for some particular terror, it can be done just less than 1 second, very good result. If we repeat the same query for the original table, it takes more than 1,000 times longer. So it's expected result of using materialized view. But what about insertion speed and influence of materialized view on insertion speed? Adding standard PageBench test with and without materialized view. Without materialized view, we get about 10,000 TPS, and with materialized view, result is 140 TPS. So. And what's worse, if we add one more view, then the result is 70 TPS, so 2 times smaller. And for analytic, we need much more views, so we can expect that performance will degrade proportionally number of views. I have performed some investigation where we spend most of the time, and the first result was that we need indexed for materialized view to make incremental update executed efficiently. Maybe not so obvious that we need to create view for materialized, index for materialized view as for normal tables, but without it, speed is much worse. Adding index allows to increase speed almost 2 times, but it is still 7 times worse than without view. And the exclusive lock of materialized view is another showstopper. It completely kills concurrent execution, and so 10 parallel clients are working with the same speed as one client. Why this parallel work, exclusive lock is needed? Consider just simple materialized view, joining data from 2 tables. And let's see 2 concurrent transactions which insert data in these 2 tables. As far as each transaction is using its own snapshot and does not see results of other transaction, we get first transaction update view in this way and second transaction update view in this way. And the result is incorrect because we lose one record. It can be prevented by exclusive lock, but this lock exclude parallel execution, so we have to find some other solution. I don't know such solution yet, so let's think together. And finally, conclusion. JIT almost eliminates need is a vectorized executor. It doesn't mean that speed cannot be improved. For example, I have another extension VOPS, which is faster than vanilla Postgres, more than 6 times on the query 1 from TPCH. But it requires creation of special projections, and it's not so trivial. Second, the LSM index allows to combine high insertion speed and fast index scans. So if index does not fit in main memory, then SAM is must-have. Undo storage significantly increase update speeds by making it possible to perform in-place updates and reduce, avoid write amplification. And unfortunately, current implementation of incremental materialized views significantly increase speed, and so it's making not possible to use them for OLAP and OLTP. This is a list of links to the extensions used in this presentation, and now I'm ready to answer your questions.